A simplified diagram of an electric current flowing through a conductor is displayed. Diagram A has negative charge carriers. Diagram B has positive charge carriers. Existence of majority charge carrier is typical of an extrinsic semiconductor. We will consider semiconductor at a later stage. Magnetic field direction is directed into the plane of this display. A simpler method of analyzing the direction of magnetic force experienced by a charge carrier is using Fleming's left-hand rule. Click and drag the left hand and place it on the negative charge in diagram A or the positive charge in diagram B. Observe the direction of the force acting on the charge. Did you notice that both the charge carriers on diagram A and B deflect the charges on the same side of the conductor? Why? Answer: yes. This is because both the charge carriers experience magnetic force in the same direction. The voltage undoubtedly is very small and requires a sensitive voltmeter to measure. E. H. Hall in his experiment managed to measure a very small voltage. Click the derivation button to observe how Hall voltage is derived after an equilibrium condition is reached. Click the derivation button to view the expression of Hall voltage. Name the dimensional parameter of the metallic strip that was not applied in the final expression of Hall voltage. Answer: width d. What changes would the expression above take if B is not perpendicular to the surface of the material? Answer: the expression for B would be B cos theta, where theta is the angle between the normal to the plane and B. Click the magnetic field B so that it makes an angle of theta with the normal. Click the Check Expression button to view the modified expression. Hall voltage is inversely proportional to the thickness of the film strip T and the charge carriers per unit volume N. What kind of conducting material would have a significantly smaller value of N? What effect will this have on the Hall voltage? Answer: semiconducting material like silicon and germanium. Hall voltage is bigger. A rectangular copper strip measuring 1.5 centimeters wide and 1.0 millimeters thick carries a current of 3.0 amperes. A 2.0 Tesla magnetic field is applied perpendicular to the strip as shown. By using the Fleming's left-hand rule, determine which side of the copper strip is negative and which side is positive. Drag the positive and negative signs and place them at the appropriate sides of the copper strip. Drag the voltmeter and place it across the copper strip. The charge density of copper, N, equals 8.48 times 10 to the power of 28 electrons per cubic meter. Calculate the resulting Hall voltage. Click the Calculate button. This value should correspond with the measured value of the voltmeter. Based on the answer for Hall voltage of 0.44 microvolts just now, calculate the electron drift velocity. Click the Calculate button. Notice that the width d of the copper strip is used here. Summary. Hall voltage is given by VH equals BI over NTE. Hall voltage generated by a metallic conductor like gold or copper is in the microvolt range. Drift velocity Vd of electrons in a conductor can be determined by Vh equals B Vd d. Hall voltage has a different polarity for positive and negative charge carriers. The determination of N-type or P-type semiconductors can be achieved. A modern Hall effect device uses semiconductor compounds to produce a large Hall voltage. This device, commonly called a Hall generator, consists of a thin circular plate or film of gallium arsenide or indium arsenide to which 4 electrical contacts are made. Since semiconducting compounds do not have a large quantity of free electrons or holes, the value of N in the Hall voltage expression is significantly lower. Let us look at a simulation of Hall effect in a semiconductor. The example in this simulation uses gallium arsenide as a semiconducting material. View its properties shown above. Now we introduce a magnetic field B perpendicular to the surface of the gallium arsenide film. Click the Magnetic Field B button. Observe the simulation. What is the majority carrier in this model? How do you classify them? Answer. Electrons are the majority carriers. This semiconductor is classified as N-type semiconductor. Compare the Hall voltage between metals and semiconductors used as Hall generator. From the formula of Hall voltage, what was the one single factor that caused the Hall voltage to be significantly larger in semiconductors as compared to metals? Answer. N, the quantity of free charge carriers per unit volume. How does drift velocity affect Hall voltage? Answer. Different semiconducting compound has varying values of N. Electron and hole mobility will directly affect the drift velocity of charge carriers. Drift velocities carriers in metals are far smaller than that in semiconducting materials like silicon or even gallium arsenide. In metals, N is approximately 100 million times more than that in semiconductors. Electron flow is hampered as frequent collision occurs. This reduces electron mobility and therefore the drift velocity is drastically reduced. Click on each property to compare the properties of conductors and semiconductors in Hall effect. From the comparison above, can conductors be used commercially as Hall generators? Answer: no. Summary: the generation of a significantly large Hall voltage can only occur in a semiconductor. For a conductor, electron drift velocity is small. In a semiconductor, electron drift velocity is higher. This is caused by A. High mobility of charge carriers, B. Lower rates of collision between charge and lattice atom, C. N is smaller. One use of the Hall effect is in the measurement of magnetic flux density or magnetic field. A device known as a Hall probe is used. This is a long probe with 4 wires connecting it to a meter. The multi-pin connectors are plugged into a Gauss meter that recalibrates the Hall voltage into magnetic field B units. Click the Magnify button to view the connections to the semiconductor strip, which is encased at the top of the stem. This device is called a transverse Hall probe. The probe needs to be rotated by the user so that the magnetic field B is at best perpendicular to the surface of the strip. Let us see how a transverse probe is used to measure magnetic field near the ends of a bar magnet. Click the bar magnet button. Now drag the magnet vertically away from the end of the probe. Observe the reading on the Gauss meter. Why does the reading drop? Answer: the number of flux lines passing through the semiconductor strip on the Hall probe decreases. Magnetic flux density that emanates from sources are sometimes unpredictable in its alignment. An axial Hall probe measures magnetic field in the direction towards or leaving the axis of the probe. Look at the diagram of an axial Hall probe. Click the Magnify button. How many terminals are there? Answer: 4 terminals. If an axial Hall probe is placed inside a solenoid, the magnetic flux density inside the solenoid can be measured. Click the solenoid button to view how an axial probe is used. Observe the reading on the Tesla meter as the probe is moved axially inside and outside the solenoid. For comparison, laboratory bar magnets have magnetic flux density of 2.5 Tesla at ends. The Earth's surface magnetic field is 0.5 times 10 to the power of minus 4 Tesla, parallel component. Click the expression button to view how a Gauss meter is calibrated from a millivolt meter to measure magnetic field B. By measuring the Hall voltage, magnetic field B can be calculated. By measuring VH, B can be calculated. This is the design methodology used in a Gauss meter or a Tesla meter. If a strong magnetic field needs to be measured, the current I supplied from the Gauss meter can be attenuated to a smaller value. Therefore, a current control mechanism is needed to be incorporated into the design of a Gauss meter. By measuring Hall voltage, charge carrier density N can be determined by the expression above. By measuring Hall voltage, drift velocity of charge carriers in a conductor or semiconductor can be determined. Click the drift velocity button. Hall effect sensors can be used to measure magnitude of current flow in a conductor. The sensor measures the magnetic field generated by the current. The device shown above is a clamp meter. It can measure AC and DC current up to a magnitude of 1000 amperes. In a digital clamp meter, two Hall effect sensors are placed on both ends of the jaws of the clamp meter. The current flowing in the cable generates concentric magnetic field. When magnetic flux passes through both sensors, Hall voltage is generated. A battery inside the meter provides a steady current flow through the Hall sensors. The clamp meter measures the magnetic field B and thus the current I that produced the magnetic field. This linear proportionality between I and B is used in the design concept of a clamp meter. Two semiconductor film samples A and B are shown. One of them is an N-type semiconductor and the other is a P-type. The polarity of Hall voltage can tell us which sample carries positive charge and which one carries negative charge as their majority charge carrier. Based on the voltmeter readings and paying attention to the polarity of the voltmeters, decide which one is the N-type and which one is the P-type. We will first decide which side of each sample is positive and negative. Click and drag the charge on the side polarity selection box over each sample edge and drop them in the correct side. Next, select the correct charge and direction of deflection of the majority charge carriers and place it over the center of each sample. Finally, select and drag the semiconductor type and drop it on each sample. Summary. Two semiconductor film samples A and B are shown. Hall effect is applied in numerous applications. They are used as Hall effect sensors to measure magnetic field or magnetic flux density in a device called a Hall probe. To determine the average drift velocity of charge carrier (VD) in semiconductor research. To determine charge carrier density N in a conductor and semiconductor. To measure remotely current in a live wire using a device called a clamp meter. To determine the polarity of charge carriers, negative or positive, in a conductor and semiconductor. To determine the poles of a magnet.